We have a basic structure of an Arduino code on the screen. So any microcontroller or any embedded processor for that matter has two segments of code. The one segment runs only once. It is used for setting up things or configuring things. The other part is for doing a certain task again and again inside a loop in a iterative manner. So the first thing in Arduino terms, it's called as setup function. It's void setup. And the second function is called void loop. Setup runs only once, while void loop runs every time. It runs again and again. It is a loop. The statements will get executed from the top to the bottom one by one, and again from the top to the bottom one by one, and so on. It is an infinite loop. So yeah, when it comes to controlling DC-DC converters, we need to have two functions basically. The first function is to produce a sawtooth waveform. That is action item number 1, which is done in this setup function. How is it done? We will see in the upcoming videos. By what feature is this sawtooth waveform achieved? It is achieved by using timers and counters. We configure the timer in a certain way so that it produces a sawtooth waveform of desired frequency. Whichever frequency you want, it will generate a sawtooth frequency according to that value. The second part is producing a duty ratio so that value will cut this and it will produce you a PWM on the contrary part. Now the second task is to generate duty ratio, and that is done in void loop. So once you set up a particular frequency, the sawtooth wave gets generated in the background automatically forever. It's not like you want to generate the sawtooth itself inside a loop. That's not how it happens. You configure the timer registers in a certain way such that this sawtooth of your desired frequency keeps running in the background forever. So you have to set up everything. You have to configure the registers only once to obtain the sawtooth waveform, and it will generate the sawtooth waveform forever. However, when it comes to obtaining the duty ratio, you need to do at every loop. Why at every loop? Because you need to keep monitoring the voltage every then and there, every 50th microsecond or every sampling time. You have to monitor the voltage and then produce a duty ratio accordingly. Then it will act on the plant, reflect again. The next sampling interval you will take. After one sampling interval gets over, you will take another sample, process it, produce a PWM. So this is a iterative process, it's a repetitive process. So calculating the duty ratio will be placed inside a loop. Now let us move to study the segments of Arduino code in detail. I'll just give a quick glance of how long this portion is. So we will first discuss what are the basic segments. Initially in any Arduino code, we need a section for declaration of variables. Maybe you are using R1 as 30 kilo ohm, R2 as 7.5 kilo ohm, something like that. So you may use some variables. You have to initialize those variables, and that's the thing that happens inside this variable declaration. When it comes to void setup, you basically have only one aim, which is to configure your timers appropriately and keep producing the sawtooth in the background, so that in the loop, when you calculate the duty ratio, the matching occurs and it will produce a PWM accordingly. So this is the special task here. Declaring pins and their modes of operation, it is obviously evident in every Arduino program. We know that pin number 10 should be in output mode, or pin number 8 should be in input mode. Whether it's a digital pin or analog pin, all those sort of information will be contained in this section. And in this section, there are some registers. There are some timer registers present in Arduino, and we will configure those timer registers according to our need to obtain the discrete sawtooth waveform, which is like this. Now this is achieved here. These are the two main things that will be achieved here. Apart from this, if you want your ADC to operate at a better speed, by ADC we mean to say analog to digital converter. If we want your analog to digital converter to operate faster, you can again configure some registers. There are some registers mentioned specifically to control the ADC. When it comes to configuring the ADC, it is always a balance between accuracy and speed. Accuracy determines how accurate your data is. If you are converting an analog voltage into a digital number, how accurate that number you are getting is. It's a balance between accuracy and speed. When you want greater accuracy, you will have to lose speed. When you want faster functioning, you will have to lose accuracy. It's a trade-off between these two. So there will be a separate clock for this ADC, and you can configure the frequency of that clock. Based on that, your ADC's speed will be decided. Obviously, inverse to that, your accuracy will be decided. Moving on to the void loop. First thing is, this will actually be our algorithm. That's why I have put everything in boxes here. The first step is to sense the output voltage by using a sensor that may be in the hardware. Sense the output voltage, convert it into a number, and then you give it to the microcontroller using analog read function. This is our first task. First task is to sense the output voltage. Once you sense the output voltage, your V0 is done here. Now we are going to compute the error. How do you compute the error? E equals Vref minus V0. We write a simple code like this, and then we compute the error. Now my Vref has some value. Either I can put E equals 12.0, which is my output voltage, minus V0, and V0 will be computed here every time, this directly. Or you can go up in this variable declaration section, you can give maybe float V underscore ref equals 12.0 as a command. Either of these things will work. Try to minimize this sort of thing due to computation issues. It's better if you give direct values here. So for understanding, I am writing E equals Vref minus V0. Once error is computed, remember the block diagram, what we do next? We compute the duty ratio. This error is basically given to a controller which will produce duty ratio. Our entire controller is mimicked by a difference equation. Let me write it here. Your controller action is mimicked by difference equation. And that difference equation looks something like this: d previous plus ki into ts into e plus e previous upon 2. It may look something like this. Now, is this enough? No, we have to saturate the duty ratio. For saturating this duty ratio, you may have something like this. If my duty ratio is greater than 0.75, hold it at 0.75. Else, if my duty ratio is less than 0.25, hold it at 0.25. This is the exact statement of your duty ratio saturation. Don't go for 1 and 0. Go for practical values. Don't go beyond 0.25 in the lower end and above 0.75 in the upper end. If we are doing some boost derived topology, please don't go above 0.55 or 0.57. Anyway, it depends on your duty ratio also. Try to limit your duty ratio to 0.55 or 0.57. Next step is, once you compute this duty ratio, you will have to store it in a register. Why do you want to store it in a register? We will see in the next video in detail. In short, I'm telling you, there may be some register which may be a 16-bit register or a 8-bit register or something. Basically, it can store only zeros and ones. Microcomputers can store only zeros and ones. So you need to convert this into proper zeros and ones and then store it inside. So that task needs to be done. This register will contain your duty ratio value. We'll see detailed functioning in the next video. And after this is done, very important, you will have to store your current values of duty ratio and error so that it will be available for next iteration. Because in this difference equation, you will have one term called as E previous and another term called as D previous. What does previous mean? Previous mean it is the value which was available for you in the previous iteration. So you have to store these values at the end of every iteration so that it will be available for the next iteration. So once you compute your D here, store it in the D previous. And same way, once you compute your E here, store it in the E previous. So that becomes next thing, but do this in the last only. Do not do this anywhere in between. Otherwise the value will get manipulated in a wrong way. So do this at the last. So now all these statements will run one by one and your controller will go again to the top and then it will start doing all this again. And this infinite loop will keep running again and again. So it will take an input, compute the error, generate the duty ratio, saturate it, store it in an appropriate register so that your PWM action will take place, and store the current iteration values for next iteration. Again go, take a sample from the output, do all these processes again, produce a PWM accordingly. So this is how Arduino program structure basically looks like.